So this is what happens when you don't have blameless postmortems. But I apologize, I won't be sort of mobile around the stage very much here, but happy to be here this morning. So we have a complex systems problem, and we need to talk. How many folks have heard of or are familiar with this framework? Maybe have seen this before. I am not a native speaker of Welsh. I believe that this is pronounced Cynefin. If you do speak Welsh, please find me afterwards and tell me how a non-native speaker of Welsh can at least get closer to saying it right. But what this framework talks about is this is a way of thinking about how difficult the problem that you're currently trying to solve is. So there's a variety of things, and the idea is that if you can understand which one of these quadrants your problem fits into, there are then different approaches for solving that problem. So the first type of problem is one that is simple. These are things where there is an obvious solution. So if I were to take this remote and let go of it and say, what direction is it going to move? That it's going to fall to the ground, right? That's pretty obvious. It's got a simple solution. And so if you have something, you just do the obvious thing, right? These are generally not the types of things that most of us deal with on a day-to-day in our jobs. Complicated problems are ones where the solution isn't obvious, but there is sort of a solution you can arrive at. And so an equivalent example would be, okay, if I let go of this remote, at a certain height, how long will it take to hit the ground? We might have to go dig up our high school physics textbooks to do that, but there's a right answer, meaning that I can actually analyze this thing and come up with a solution that will be predictive of what's going to happen. Okay, so these are complicated problems. The next level are complex problems, and so these are ones where or systems where we can't necessarily have predictive knowledge of cause and effect. We can understand what happened afterwards. So if this was a tennis ball instead, and I was to say, hey, I'm going to throw this tennis ball out over in that direction, where will it land? This could be a complex problem because somebody could stand up and catch it. It may bounce off of a number of different things in sort of unpredictable ways. But if we were able to have, say, a video recording of that going on afterwards, we could say, okay, well, he threw it over there and it bounced off the wall and then bounced off that person's head and then rolled under the chair over here, and we would actually be able to understand how it got where it got, right? But it's hard to predict ahead of time what's going to happen. The next level is our chaotic systems, where like you can't even understand cause and effect in these sorts of systems. These are very difficult systems to go and deal with. And so this would be something like, hey, I'm going to throw the tennis ball out there, and while we may have video recording of that going on, we're going to turn out the lights while that's going on, and we're going to turn them off when it's done. We can see where it ended up, but we're not really sure how it got there or why, right? That's what living in a complex system is like. So in this talk, what I'm hopefully going to convince you of is that the systems that we deal with on a regular basis here in the technology industry are in fact complex systems, and that as a result, because of the sort of difficulty of these types of systems and problems, we have to actually adapt our approaches to deal with them successfully. Okay? Now, it turns out there's a whole branch of science called complexity theory that studies complex systems. And so what I want to do is I want to run you through a few of the sort of core characteristics that complex systems have, and then see if these seem familiar or to your regular experience. So one of the first properties of complex systems is that they can exhibit cascading failures, right? This is the idea that one part of the system might fail, and then that causes another part of the system to fail, and then that causes another part of the system to fail, and so on, right? Anyone have experience with one of your services failing and then Other services failing as a result? I mean, raise your hands if you've had that happen, right? That's a lot of people, okay? This is pretty familiar. I think that, there are actually great resources. One of my favorites is a book called Release It by Michael Nygaard. And in this book, and actually the second edition was recently released. I'll admit I've only read the first edition, but that was pretty awesome. And I think I highly recommend this book. But they have a bunch of what he describes as stability patterns. So these are just patterns you can apply to your systems that will help to prevent some of these cascading failures, right? The big idea is to try to, if there's a failure going on, try to contain it and keep it in one area. And so he's got a lot of great patterns you can apply to your systems as a result of this. Complex systems are also often open systems, which means that they don't operate in isolation, right? They operate in the context of an environment. And there are interactions with the outside environment. So, how many folks run services that have customers? How many of your customers work for your company? I mean, some people run internal products, so that's fine. So this is a good example where, hey, there is all kind. How many people have had a production incident caused because your customers did something unexpected? Right? So this is a really good example of the types of things that go on, right? There's all this stuff that happens outside even of the technical systems or even the techno-social systems, right? I think John Allspaw is maybe where I first heard that term. But are the systems that we are used to working with, we're actually part of those systems, right? The teams that actually cause changes to happen, right? Like, I wrote code, I pushed it to production, I just changed the system. I'm part of that system, right? And so your processes and the things that you do on a regular basis are also part of the system. Other really good examples, we also run in the context of an industry, right? Where, there's tons of open source that's going on. Right now, you can't actually, I think, have an effective technology strategy and completely ignore open source. That's really rare, right? Open source is where a ton of innovation happens. It's where a ton of collective development happens. And it can be a real business risk to not pay attention to that stuff and to figure out how that fits in. This is not to say like you use open source for everything, but if you're not at least considering it, you're probably missing some things. We have open standards, right? Even the networks that we work on, right? BGP is a good example of there's no one central authority that runs BGP, right? That's a collaboration among multiple network operators to make the internet work. And so those are other examples of interactions that we often have that sort of extend outside our direct systems and behavior. So complex systems also have memory, and this is the idea that the complex system can remember things that happened to it in the past, and that affects the future behavior. And I mean, well, our servers literally have memory, as do we. We also have memories. How many people have ever told a production war story to somebody else in your company, right? And so that's a good example of like, hey, I remember this thing that happened. I'm actually passing that knowledge on to one of my teammates. That might affect that teammate's behavior, right? Because hopefully we're good at learning from other people's mistakes before we have to make them, ourselves. But there are all kinds of behaviors here. Any system that has a database is a very straightforward example of this, right? Where, hey, the reaction to a request might depend on updates that have happened to the database in the past, right? So for sure, this is where we are. Now, something that's really interesting is, and I think especially when we start to think about the fact that our systems are comprised both of the technical systems and the people that interoperate with them, I think there are often opportunities to take more advantage of memory than we do. This is, I actually found this. So this is a meeting, or the minutes of the proceedings of a general meeting of the citizens of Philadelphia. So all of the citizens of Philadelphia apparently had one big meetup, and they wrote down the minutes. And so how many people write down minutes of the meetings that they attend? right? A handful of folks, so good for you. So back in, when was this? 1792. So if this was a good idea in 1792, when it was actually a lot harder to write down and disseminate information, why aren't we taking advantage of this now? Especially because lots of the things that we do impact others in our department that couldn't be in that meeting. Sometimes it's actually just a direct colleague on my team who couldn't be at the meeting, right? Had a doctor's appointment, I couldn't be there. There are lots of good reasons here, but there's lots of other people that may not even realize that that meeting was happening or that a decision was made that they care about. And so writing things down could be really useful. Anybody recognize this? A handful of folks. So if you don't recognize this, this was the Google Search Appliance. So this is a product that Google, it's been discontinued, but the idea was they would give you a server, you would rack it up in your data center, and it would go index all your stuff. So you could have internal Google search of all of your internal documents. So how many people have sort of multiple systems where they put information in on a regular basis over the course of their day, right? Like, we got Slack, maybe Jira, maybe GitHub, source control, comments, never mind wikis, things of that sort, right? Like there's all kinds of information that are going on. How many people have a federated search across all of those things? Right, so there's tons of information that we're not taking advantage of. We're actually, in some sense, handicapping ourselves as a complex system by not taking advantage of some of these things, which in some cases have technical solutions, which is kind of interesting. So if you're interested in this federated search problem, actually this is something I've been thinking about that sounds like a pretty good open source project. So if you're interested in doing that, come and find me afterwards. Complex systems often exhibit nesting behavior, which means that the components that make up a complex system are often complex systems themselves. And so in a technical setting, for example, that means it is turtles all the way down, right? It means that hey, maybe I've got a region of my cloud provider that's a complex system. Availability zone within that region, that's a complex system. A particular service, right, which may be composed of multiple microservices, or even a given microservice may also have multiple processes or threads, and we can go all the way down and understand that actually lots of things all the way down to a pretty low level exhibit a lot of these behaviors of complex systems. So this is not just something where it's like, hey, we can sort of paint the magic deal with complex systems brush up at the top level of thinking about these things. This is actually something that's pretty fundamental that we need to start to think through. Complex systems also have dynamic networks of interactions where connections are formed and broken, and sometimes some of those connections are close and some of them are far. This is actually the way our brains are set up, right? So we have tons of neurons, and neurons both are connected to other nearby neurons, but some of them also have really long distance connections as well to other parts of our brain. And so what's really interesting, and actually recently, I think we've seen some tools show up that have actually given us a better opportunity to do this in our organizations. So many people have heard of Conway's law. Only a few folks. Okay, so this is all right. Hold on, we got to say this total sidebar on Conway's law for a second. So Mel Conway, who by the way still tweets, but I think sometime in the 1960s, published a paper which described the way human committees design stuff. And what he said was that a group of people is constrained to design a system that matches the communication patterns of the people who designed it. And so an easy way of understanding this is if I have 3 teams that are developing a compiler together, I will have a 3-stage compiler. If I have 3 teams that are building something, I'll have at least 3 microservices in my architecture, right? Steven Sinofsky once summarized this as you ship your org chart. And really in a lot of companies, especially large companies, we still rely a lot on organizational structure to communicate things around the company. But we actually now have tools that allow for this type of much more dynamic forming of relationships and communications, right? Slack channels. I can go join a Slack channel. I can leave a Slack channel, right? I can go find the Slack channels, go participate when I want to, and then come back off. And not everybody in that channel has to be on my team, right, or even part of my department, right? We can have Slack channels that are communities of interest around a specific topic. Same thing with GitHub, right? Like, or your internal source control system, right? Like, you can go find other teams' projects. You can open pull requests. You can open feature requests. You can identify issues, right? And again, you can make that connection for a while, establish communication, and then back off, right? It's the open source has actually trained us and pointed a way that we can do some of these things as well, and start to take advantage of these new tools that we have. This is a really interesting one, and I think one of the most compelling things about complex systems. So these are termites, and an interesting thing about termites is that they can build these really elaborate termite mounds, right? That are really quite large. Even though an individual termite is sort of well, it's not even relatively straightforward, right? Because even a termite is a complex system. But I'm pretty sure there's no chief software termite, right, that is designing how this thing is working. And in fact, the termite mound arises just out of the interactions of the termites themselves, right? And so in particular, there's emergent behavior. And what this really means is that when you think about the behavior of the system, you can't actually understand all of its behavior just by understanding the behavior of the individual components. So how many, I think we asked this before, but how many people have had an outage in your service that was caused because some other service changed, right? Or your customers did something unusual, right? And so how many people, think back to the last production outage you had. For how many of you was that a surprise? Right? Even if it was a change-related incident, right? I went and I pushed a change in production and it caused an outage. I was probably really surprised that caused an outage, right? A big part of a lot of after-action reviews where we understand what's going on is having people say, I didn't know that would happen, or I didn't know it worked that way. So if you've been following John Allspaw and the Stella report that he published, was it a couple of years ago now? He talks about this principle of dark debt, which is the idea that we actually don't have full understanding of what's going on. This is actually, I think, one of the critical things that makes dealing with complex systems really hard for us. My uncle is a retired professor of anthropology, and one of the things he said to me one time is one of the main things holding back human society is that we only have 1,400 cubic centimeters of brain. Like we actually have finite processing capabilities. And what's really interesting is that we are building systems that it is literally actually impossible for one person to understand because we simply don't have enough computing power to understand all of the things that are going on here. So, but nonetheless, there are plenty of successful companies that make lots of money and make their customers happy as well. And so what do we do about this, right? So a big part is that if our systems are going to exhibit surprising behavior when they get changed, it's really important for us to have some good indicators of what's going on, right? Like all of those gauges in a cockpit, right? Like these are all in a plane that actually like mostly flies itself, right? And so, think, what kind of information do you have about your systems? This is really why, whether you call it operational visibility or observability, that's why this is so critical for modern systems these days, is because our systems will surprise us. And we need to be able to see what is going on, because what's going on is likely, if we care about it and are sort of anxious about what's going on, it's because something is going on that we didn't expect. So it's really important to lean into this type of instrumentation. Complex systems also have a property, which we'll talk about, of where you can have snowball effects, right? So just like if I start a snowball at the top of the mountain, I get an avalanche at the bottom. Complex systems often have nonlinear effects, right? So there's the idea that a small change can end up having a large impact. Again, because there are unexpected things, we have the cascading failures where things are interconnected by all these networks of interactions. So any change can actually have a pretty large blast radius. And so what that means is if the impact of a change can be magnified, that suggests that we have to take sort of a different strategy here, right? Which is that maybe we want to make smaller changes, right? So if that's bad when it gets amplified, it's not as bad as if we made that same change in a big way and it got amplified, right? So we want to start making smaller changes because these could be unpredictable. But at the same time, we still want to get stuff done, right? It's still really important to ship features and remain competitive in the marketplace. And so if we're going to have smaller changes, but we want to get the same amount of stuff done, guess what? We have to do those changes more frequently, right? So this is all about smaller changes more frequently. And that's actually just driven directly by the complexity of the systems that we have. This is really the only safe way to do this. And so this is why things like continuous delivery are so important. And leaning into being able to make a small change, get that out to production. This is why we do things like canary deployments, right? Where I can shape traffic so a new version of a service only gets seen by a small portion of my customer base. And then as I get more confidence that that change is working well, rolling it out more effectively, right? These are, here at a DevOps conference where, a lot of times we talk about processes and tools. This is one of the big things that we should be thinking through is how can I make smaller changes and get them out to production more quickly? All right, so those are sort of some of the core properties of complex systems. Hopefully I have convinced you that these are the types of systems that you actually go and work on a regular basis. And so I kind of want to make an observation, which is that, we have, we're talking about DevOps, right? As sort of bringing together two communities, right? The dev community and the ops community. And when I think sometimes about, saying what do we do? Like, what are we actually doing right here? It's like, okay, I build and operate software, right? But the reality is, this is a way of thinking about the problem that actually assumes that we're in a complicated domain. This is the idea that I can make a code change, and I actually know how that's going to behave in production, right? Just like I can get my high school physics textbook, I can drop the remote, and I can tell you how long it's going to take to hit the bottom. There was a time when the software industry was more like a complicated problem, right? Back in the days of shrink-wrapped software, right? Where, hey, that program only runs on one computer, right? And it fit on 3 5.25 floppy disks, right? It's like, I believe there was one person who could actually understand everything that was going on in that software, right? But now the software that we write interacts with all kinds of things, right? If we run mobile apps, those run on hardware that we don't directly control, right? To some degree, like even running in a cloud provider, right? Like we don't control all of the things that are going on there, right? There's lots of interactions. Everything's on, almost everything's on the internet, right? We can have bad actors, right? Like the recent, we see DDoS attacks, right? That actually interrupt a lot of service. And so I think my main thesis is that, the software industry started in this complicated problem domain, and a lot of the ways that we think and even talk about what we do trace their roots to this way of thinking about the problem. Just the fact that we say build and operate, or that we have dev and ops as separate things. And I think we can't do that anymore. And I think this is actually one of the main drivers of DevOps. Is that the reason these groups of people need to come together and collaborate much more closely is that we don't build and operate software anymore. What we do is we evolve production. And that's actually the right way to think about what we do. And so it's that mindset shift where we realize that, hey, production is this complex system that when we change it, it's going to have unpredictable behavior, right? That things are going to come talk to production, right? Whether those are bad actors or customers doing surprising things, or even just a security researcher that reveals a vulnerability in a key project, right? Where it's like, hey, anybody remember Heartbleed? Right? It's like, hey, we kind of have to go and like do a bunch of stuff we didn't plan on doing, right? So I think this is the right way to now think about the way that we're working. And I think in some ways, when we think about DevOps and the things that we talk about here, a lot of the reasons behind why we're having these conversations and why this is so important to many companies is that whether we explicitly acknowledge it or not, I think through experience we're beginning to understand that this is the right way of thinking about what we do. So just to wrap up, as I said, we have a complex systems problem and we need to talk. First part of the solution is admitting that you have a problem. And so, I think if there's one thing that you've taken away from this talk today, it is recognizing that, in fact, our systems are complex and that it's important for us to realize that as a result, that they require different ways of dealing with them. Our systems are not merely complicated, in those things. And so we really do have to adapt. And generally, the main takeaway is that Dev and Ops are not separable activities. In fact, you can't separate these things effectively because it's really on the sharp edge of production changes that's where all of the action is, and we have to orient ourselves around thinking through interacting with that system and evolving it. So with that,
you've got time for questions.
I've got time for questions. So thanks. We make the argument that the software development lifecycle is chaotic. So you could make that argument. I think that's kind of a bleak worldview, which it may be right. In a chaotic system, you basically just have to try stuff and hope it works. I'm not sure we're quite there yet. I think we do. There are lots of good examples, and I think we're going to see more and more control theory brought into the software world. So, referring back to that airliner, with very complex autopilot, there's actually a whole history of pretty effective control systems. A really good example that I like to think about sometimes is there's something called a PID controller, PID. And this is able to effectively control a system without understanding how it works. And so a good example would be the cruise control in your car, right? That effectively works this way, right? So it's like I know I have a target speed, and I just compare my current speed to the target speed. I don't have to understand, and if I'm not going fast enough, I push down on the accelerator some more. And if I'm going too fast, I let off the accelerator. And so I don't have to understand. I don't have to understand how the engine works. I don't have to understand whether I'm going up or downhill or any of those things. So there are, I think, mechanisms for effectively controlling systems that we don't understand. And so I'm still hopeful. And I don't think that when we make production changes, although we're surprised a lot, we actually make a lot of successful production changes, right? Like it's not like our hypothesis about what's going to happen is, it's just not 100% correct. Right, but it's often very likely correct, right? This is why lots of these companies are able to be successful and still be in business even with this level of complexity. So I'm not convinced we're all the way to chaos yet, but I guess we'll see.
Thank you for your presentation. So first question is, what are some of the tools that you like to use to help manage your complex systems? And second, do you have the URL for the federated search GitHub project that you're starting?
Oh, no. So all right. So I'll answer the second problem first, which is I think this would be a great open source project. So it hasn't been started yet, but maybe I need to go create one. But anyway, as far as some of the tools for sort of dealing with these complex systems, I do think leaning into operation and visibility tooling is really important. So this is where things like log analysis, the elk stack, for example, is a good example of ways to do that with open source products. There are, of course, commercial products in this space. Collecting application metrics using things, for example, like Prometheus is a good example of ways to get some of those gauges and dials for the cockpit, so to speak. Distributed tracing. Again, I think that's sort of the next step beyond that, where I think you want to get some of the basics in place first before distributed tracing, where you can actually see what happened to something as it bounces around your complex system. But there are even more advanced tools that really rely more on introspection, right? So like saying like that part of my system is not working well, and can I go see what's going on with it? Interestingly, there are a lot of people that say like you should never SSH into production. And I think that's meant in the right way, which is that you shouldn't have to SSH into production to make your changes, right? The idea is like, hey, I want to drive these in an automated fashion. I should have all the metrics and things set up so that I can get some good ideas. But it turns out, guess what? There's all these amazing tools from the history of Unix that are on your Linux server that tell you what's going on with that thing. And so I think that, I think generally you should probably not be SSHing and making changes to what's going on, but I think SSHing into something to see what's going on is actually a major part of our toolbox that we shouldn't necessarily shy away from, because sometimes that's really the only way to get the type of understanding that you're looking for.
Great. So thinking of, especially like the concept of emergence, and thinking of course, like Conway's Game of Life, which, we see emergent patterns from a simple set of rules. How could, if we, because a lot of the talk was thinking about shifting the approach or mindset. And so how would that impact software architecture design if we approach things not intending for outcomes, but intending for like that some patterns will emerge from a core set of principles?
Yeah, so this is something I think about a lot because especially in my role, they call me the chief software architect, but there are thousands of engineers working, in the organization that I'm part of. I guarantee I don't know even half of the ones that exist. Right? I don't even know they exist. Right? It's not possible to do this. So I think for architecture, I think what you start to think through is starting to think through more about rules, right? And like, you mentioned the game of life, right? And how can I tweak rules in such a way that I can cause the right properties to emerge is the way to start thinking about that. One of the things that we've been working on inside Comcast is we have an architecture guild. This actually works a lot like the IETF, but as we see the need for trying to drive a little more commonality in some parts of our tech stack, we've actually opened that up, and there's a grassroots effort that goes into it. So we say like, hey, we'd like to pick a CI/CD system, right? Like if you care about it, you can show up and participate in that decision-making process, right? And we had hundreds of people. That's an example of one that we did recently. And so we had hundreds of people that showed up to provide their use cases, to suggest things that we could evaluate. And so I think it's more like leaning into the advantage of the complex system, which is that I'm going to have a lot of independent sort of interactions because like an individual team that's running a microservice, they're a complex system. And so that's where I think through things like the federated search, right, and the meeting minutes, and how do I sort of take advantage of the broad learning that's going on? How do I think through examples of things and where, in some sense, I sometimes say a big part of what I do is reverse engineer the operating system of the company that I work for. Right? So you need to understand how are decisions made, how do budgets work, how do hiring decisions get made? Because guess what? All those things can impact the way that your system evolves and the way that your teams behave. And sometimes just, for example, figuring out that, if I take this service and instead of it having its own budget, I change that so that they charge their internal customers back, right, for what they do. It's like, just that one change can all of a sudden induce all of the behavior that you're looking for. And so it is thinking more in terms of the rules of interaction and the rules of engagement is, I think, what sort of architecture is becoming these days. Yeah, so the question was, release it sounded really good for those stability patterns. Is there a companion volume for complexity theory? This is where I admit to you that I relied heavily on the Wikipedia article for this. Which I think actually I would recommend that you go there. Like there is actually a lot more information there. We're not complexity theorists, right? So while certainly like there's tons of textbooks, I don't have one that I can recommend to you. I do think that it is certainly worthwhile to go and understand those sorts of things. For us, I mean, I've been more satisfied with just sort of recognizing that we're in this domain now. And to some degree, some of the solutions are going to be specific to the particular setting that we're in, right? So it's like, okay, GitHub, right? Okay, that's a specific thing for source control, right? Do other industries, do other complex systems have something that works exactly the same way? I don't know. But that's one that exists in our environment that, that we can think through how to interact with.
All right, thank you very much. Let's go for John Moore.